Hello everyone, we are from Computing Department of Hong Kong Polytechnic University, and today we will demonstrate how we use Simulink to simplify the implementation of robotic system. Our system is a 3-axis robotic arm controlled by 3 stepper motors. To control the system, we used Arduino along with RAMs, a most widely used board among 3D printer community. Due to limited computational resources, Arduino cannot be used to implement complicated computer vision and machine learning algorithm. We decided to use Raspberry Pi to perform computationally intensive tasks, but still we need to write our code and communication protocol which can be time-consuming, prone to errors, and hard to debug. To avoid these issues, we use ROS, a popular robotic operating system for communication layer, and Simulink for algorithm implementation since it provides extensive support for ROS through Robotic Toolbox and Arduino and Raspberry Pi through hardware support packages. To control stepper motors through Arduino, we need to use timer interrupts. Unfortunately, the Arduino support package does not support interrupts yet. Similarly, there are no blocks for ROS messages. Fortunately, this was not an issue since we can use the S function builder to link external C libraries to our Simulink model. Using the S function builder, we linked Arduino and ROS lib to our Simulink model and implemented our own blocks for stepper motor controller and the ROS node. By using model configuration panel, we can choose the hardware board on which we want to implement our model, and by just hitting the build button, the model is automatically compiled, linked and uploaded to Arduino board without ever leaving the Simulink environment. And just like that, the first part of our implementation was complete. The next step was to implement ROS node for the Raspberry Pi. Here we will show a simple ROS node which listens to messages on a specified topic and applies inverse kinematic transformation from the Cartesian workspace to the joint configuration space, and then publish it to another topic. Our Arduino node is listening to this topic and move the stepper motor to the angle specified in the message. In model configuration, we chose ROS as implementation platform and selected the processor according to our Raspberry Pi. To automatically deploy to the Raspberry Pi, we needed to start an ROS master on the Raspberry Pi. We already installed ROS on a Raspberry Pi and set up a Catkin workspace for our ROS node. Additionally, we also installed ROS serial library to communicate with ROS node running on Arduino. In Simulink, we made changes to the network configuration accordingly. Again, just like Arduino, pressing build button will automatically generate C code for the ROS package. Copy it to the Catkin workspace on Raspberry Pi and build the package. Now our model is converted to an independent ROS package. We can take our Raspberry Pi anywhere and run the package without needing a connection to a Simulink installed PC. Now I will show you how we use Arduino and Raspberry to control our robotic arm. First, we programmed our Arduino, which is now listening to the ROS message and move the motors according to the angle specified in the message. Then we implemented an ROS node which takes Cartesian workspace and applies inverse kinematic transformation to calculate corresponding angles in the joint configuration space. Now we'll combine both of these nodes using ROS serial package. In this demo, you can see that by publishing Cartesian workspace coordinates to the XYZ coordinates topic, our robotic arm moves accordingly. In future, we are planning to implement our research ideas on this robotic platform, which includes attaching camera to the end effector using computer vision algorithms to guide the robotic arm, and control algorithms based on recurrent neural networks which are too complex to fit on Arduino. Thanks for watching.